Hello, my friends. So nice to see you again. So many people revisiting my channel. I hope I am really of use to them. Good to know. How are you? Today, we learn a really useful trick. Let's get started. Okay, today what I'll cover is the issue of recalibrating instruments so that their readings displayed on the field matches the value that is displayed on SCADA for the same variable. Okay. Now, in such circumstances, it is common practice to open the instrument and adjust the zero and span settings or recalibrate the instrument with a heart transmitter. Now, both of these are quite cumbersome process which involves somebody to go to the field and open up the instrument. Or sometimes there may not be a heart transmitter available around. So I have come up with a new idea how to do this, to be able to do this anytime, from SCADA in a very easy and trouble-free way. In this example, uh, we take a pH transmitter, Now, this is a particularly notorious instrument. It requires frequent readjusting. And every time, recalibrating the pH transmitter is not a good idea. So, our goal is to see how to come up with a method that can reliably achieve a two-point calibration from a HMI screen and a associated, logic in the PLC. Okay, now we begin with the equation of the straight line, y equal to mx plus c. That value c is the offset where the line crosses the y-axis or at a value x equal to 0. But in our case, we are dealing with not that point C, we are dealing with y min. So that is the value of the output when the value of the input is at its minimum. So, the slope becomes out maximum minus out minimum divided by in maximum by in minimum. All right. So we have to encapsulate this equation in a function block and we can get a very nice scaling function. So this is how you go about making a scaling block function. Okay. All you need to do is to declare the parameters for the input and output and also create a space for the signal that is being scaled. All right. So here we go. In max and in min represent the high and low values of the counts from the analog channel. So also out max and out min are for the maximum and minimum value of the scale output signal in engineering units. All right. And then in raw represent the counts from the analog channel that is connected to this block. All right. Now within this block, we have to encapsulate the same equation we saw on the previous slide. See, some PLCs like that Siemens TI portal or Semantic Manager, and then this, something from Schneider like, whatever control manager, control expert, they have calculate blocks. Other PLCs, they don't have calculate blocks. So in any way, all we need is to write the logic using either a calculate block or in the form of rungs with suitable data type conversions and things like that. I have given both examples below. These are for a guidance, but this principle can be used for any PLC. Now we continue to uh, add features. That is how to calibrate this scaling block. We have to give it features like there has to be a calibration mode wherein you can change the you know minimum and maximum values of the input signal, and also the minimum maximum range of the scaled output signal. So we also need some values for comparison, that is for let's say a known pH or a known temperature for typically 2-point calibration. So this example is for 2-point calibration. The principle can be expanded to any number of points that we will handle in a later video. Okay. Now, actually, the big difference here is that the scaled values such as the in max, in min, and the uh, you know what do you call the scaled high and low values, they need to be in out variables because we need to change them. So the function block will have to write it to them. Okay, that's only the important change. Now we discuss the logic inside the scale with calib function block. Now this has to be a function block because this has some retained variables. Whatever the maximum and minimum values of the inputs and outputs, as well as the the signals for entering the calibration mode, and all these are read write. And not only these are read write, but the raw counts, minimum and maximum, as well as the scaled high and low values, they also need to be retentive. I mean, they have to be retained after power cycle. All this makes the use of a function block necessary as a function. Using a function won't do. All right. Basically, you see the rungs here. The first rung is the scale block which we developed earlier. This scale block will scale the input signal as long as it is not in calibration mode. Okay. Now we add logic for changing the scaled high and scaled low values, and also the raw counts that are prevailing when we calibrate it at 2 points. That is, when we are calibrating the high point, we save the scaled high value as well as the raw counts corresponding uh, to that particular calibration point. And so also we fix the low value of the scaled and corresponding raw signal at that time. So, and then we also give another rung which tests the calibration. There's a way of entering the value of a test signal, that is a known pH or a known temperature, and then validating the function. The timer in that rung is provided for giving a certain time for the signal to settle down, because this is the example that we'll be dealing with is a pH meter. Now the pH readings and all take a few seconds to stabilize, typically about 30 seconds. And there is also a certain allowed margin of error, and the third rung merely calculates the error in percentage, and then it compares whether this error is within the allowed range or not. If not, then it reports an error. Okay. Okay. After making that function, we deploy it as a public instance. That is, this instance covers its usage for a given transmitter. This is a pH transmitter, as I said earlier. It is called pH DX1. There are other instruments like this. This function block deals with only pH TX1. So this is how the signals are tied. you know, there is this calibrate button that puts this block in calibrate mode and sets the calibration mode signal. Okay. Then after we are in calibration mode, we place the pH probe into a calibration buffer of 9.81 pH, and correspondingly you will notice that there is some reading, what is shown in green, the signal high column corresponding to this 9.8. Now that is the raw counts that are given by the analog signal corresponding to pH of 9.8. So we accept it for what it is, and then when we click the set high pH value, uh, we say you save this, as the high side parameters of the input and output scaling block. See, so this value of 230 counts goes into raw counts for the pH high value. Okay, and so also for the low, when we assign the when we fix the low point, that is the low pH point, the value of 4 will go to the scaled low value, and 38,400 counts will go to the raw count variable. All right. This is how the scaling block is configured. This is possible because these are all in-out variables. That is, they can be written upon within this block. Okay. Now, finally, to test whether this block is working, the calibration is satisfactory or not, we now introduce the pH probe in a solution of a known pH, a known buffer. Here it is 0, but it won't be 0 actually. There will be some value. And then we try the validate button. Okay. Now whatever the pH reading is shown here and whatever was entered here are compared. And if there's a certain error that is beyond the allowed limit of about 3%, then error is reported. Okay. So friends, that is all I have for you today. I hope you found it useful. Please tell me what you think in the comment section below. Okay. And also, please feel free to voice your suggestions and any ideas that you'd like me to discuss on my channel. And before we say bye, please spread the word about my channel with your friends and those people who are in automation. Thank you very much. See you soon.